Hi, I'm Dave Mueller, retired hydrologist from the U.S. Geological Survey and founder of Genesis Hydrotech. Now that we have finished evaluating the measured data and choosing the best methods to estimate the unmeasured areas, it's time to consider the uncertainty of the discharge. Uncertainty is not an error because to determine an error, we must know the true value. Uncertainty is a parameter associated with a measurement that characterizes the range of values that could reasonably contain the true value. A measurement with a large uncertainty may be accurate and without error, but we don't know that, so it has a large uncertainty. A measurement with a large uncertainty does not mean the measurement is in error, only that we believe the measurement is within the computed uncertainty of the true value, which is unknown. QRevInt provides two options for computing the uncertainty of a discharge measurement. The QRevUA is the original uncertainty analysis that was introduced as part of QRev to provide a qualitative estimate of uncertainty. It's a simple approach with uncertainty components estimated by the coefficient of variation, expert judgment, and simple computations. The arson uncertainty analysis is more complex. It clearly decomposes the uncertainty sources, has fewer fixed values than QRevUA, and has a better response to the measurement environment. The user can choose which uncertainty assessment they would like to use by clicking on the Options icon at the top in the toolbar and scrolling down to the uncertainty component in the options list, and then selecting either QRev Original or the arson analysis. Let's briefly talk first about the original QRev uncertainty analysis. When this is selected, the main tab will have a table listing the values of each of the uncertainty components that this uncertainty analysis addresses. The random uncertainty uses the coefficient of variation and then based on the number of transects inflates that value to a 95% uncertainty. For invalid data, it is assumed that we are within 20% of the estimated percent discharge from invalid cells and ensembles. The edge uncertainty is estimated to be 30% of the total discharge in the edges. The extrapolation uncertainty is computed as the difference in discharge from the selected extrapolation method and the other extrapolation methods, and then the average of the best four. Moving bed uncertainty is estimated to be between 0 and 3%, depending on the presence and quality of the moving bed test and the use of GPS. Finally, the systematic uncertainty is based on specifications and some work by TRDI. And note that while all the others are at the 95% level, the systematic is estimated at one standard deviation or the 68% level. The final estimated 95% uncertainty is computed as the square root of the sum of the squares. Also in the table is a column for user. The user can override any of these automatic estimates, and the final 95% uncertainty will then be evaluated based on these user input values. If you choose the arson uncertainty analysis, the table at the right is replaced by a lollipop plot. This plot shows all of the different components of uncertainty that are evaluated using the arson analysis. And the plot is to show the relative contributions of each of these uncertainty sources to the total uncertainty. In addition, an uncertainty tab will also be presented, and we'll talk about that after we discuss the arson uncertainty model. The arson uncertainty model has been published in a paper in Water Resources Research, and I certainly want to acknowledge all of the people that have contributed to the development of this uncertainty model. The arson uncertainty components are: the system was estimated to be 1.31%, which is very close to that estimated from the TRDI work at 1.5%. The uncertainty due to the compass, this is a value that is unknown, but a 1-degree compass error is assumed, and the equation 41 from Mueller's paper is then used to assess that particular bias when using GPS. Moving bed uncertainty uses the same approach as does the QRev uncertainty analysis. The number of ensembles is based on a formula from ISO. The measured discharge is a random uncertainty and is computed based on a formula. The uncertainty of the top discharge, bottom discharge, left discharge, right discharge, invalid boat velocity, invalid depths, invalid water velocity are all estimated using simulations, which will be discussed shortly. Finally, the coefficient of variation is a random uncertainty, and it is assessed using a Bayesian coefficient of variation. For the system or systematic uncertainty, this accounts for all the residual errors that remain after an ADCP has been calibrated. It represents the minimum uncertainty of an ADCP discharge measurement under ideal conditions. It is estimated to be 1.31% using data from Oberg and Mueller 2007 and from Naudet 2019. The compass uncertainty is only applicable if the GPS is used as the navigation reference. The compass uncertainty is a bias and not a random uncertainty. This bias is computed using an equation from Mueller 2018, assuming a 1 degree heading error. The moving bed uncertainty uses the same assumptions as the QRev uncertainty analysis. If bottom track is used as a reference, and there is a moving bed test that is valid, if there is a moving bed, the uncertainty is assumed to be 1.5%. If there is no moving bed, it is still assumed to be 1% because that is the criteria we use for determining a moving bed condition. If bottom track is used and the moving bed is invalid, the moving bed is unknown and the uncertainty is set to 3%. Likewise, if a moving bed test was not conducted, the moving bed condition is unknown, and again, a 3% uncertainty is used. If GPS is set as the navigation reference, then the uncertainty for a moving bed condition is set to 0. The uncertainty due to a limited number of ensembles is computed using the equation proposed by Lacroix and others from 2012 as an approximation of the tabulated values proposed by ISO 2009. The measure discharge is a random uncertainty, and it does not account for any correlation between the cells or between the ensembles. Usually this is an insignificant contribution. Practical use is still being discussed and is estimated from this equation, where the water track uncertainty is estimated to be the standard deviation of the water track air velocity data. The uncertainty of the bottom track is estimated as the standard deviation of the bottom track air velocity. If GGA is used as the navigation reference, its uncertainty is calculated using the standard deviation of the elevations from the GGA sentence. If VTG is used as the reference, its uncertainty is assumed to be 0.5 meter per second based on manufacturer's documentation. And finally, the depth cell size is estimated to have an uncertainty of 0.5%. For the top discharge, we're going to use a number of simulations and then use the rectangular distribution equation, where we take the maximum value computed from the simulations and the minimum value computed from the simulations, subtract them, and divide by 2 times the mean discharge and the square root of 3. The simulations used are shown in this table and show how the top, bottom, and exponents are varied in the various simulations, and even for the last 2 simulations, the draft is changed, increased and decreased by the uncertainty of the draft value. From that, the maximum is determined and the minimum is determined, and the equation here at the top is used to compute the uncertainty of the top discharge. Similarly, the bottom discharge is computed using that same equation and a series of different simulations of discharge. The edges are also computed using the rectangular distribution law. The simulations include the selected left and right edge discharge using the selected settings, the edge minimum, the left and right edge discharge assuming a triangular shape with the left and right edge distance decreased by the specified distance uncertainty, the edge maximum, the left and right edge discharge assuming a rectangular shape with the left and right edge distance increased by the specified distance uncertainty, and then a simulation using the draft minimum where the left and right edge discharge is computed using the selected settings with a draft decreased by the specified draft uncertainty. Potential issues with the approach used for the edge is that when edges are carefully measured and characterized, this approach can result in a substantial overestimation of the edge uncertainty. The use of the rectangular distribution law assumes that the value used is at the center of the distribution. However, for our edges, this is not typically true because the selected edge shape of triangular or rectangular is near either edge of the distribution of our simulations. Invalid boat velocity, again, uses the rectangular distribution law. It looks at 3 different interpolation options. In the first simulation, the discharge is computed by estimating the invalid boat velocities using the linear interpolation, which is automatically applied in QRevInt. Then the discharge is computed by estimating the invalid boat velocities using only the previously valid boat velocity. And finally, the discharge is computed by estimating the invalid boat velocities using only the next valid boat velocity. Invalid depths are computed in much the same way, using linear interpolation, using the previous valid, and then using the next valid. Invalid water velocities use 7 different simulations. For the first simulation, ABBA, measured discharge with invalid water velocities, are estimated using the ABBA interpolation, which is automatically applied by QRevInt. Another simulation computes the measured discharge with invalid water velocity estimated using TRDI's interpolation. The next 4 are a subset of what is used in the ABBA interpolation. It uses only the adjacent valid cell above, uses the only adjacent cell below, uses only the adjacent cells before, and uses only the adjacent cells after to estimate the velocities and discharge in the invalid depth cells. And finally, we look at shallow water, the measured discharge with no interpolation for ensembles that have no valid depth cells due to shallow depth. The coefficient of variation accounts for all of the random uncertainty. The Bayesian approach allows for the use of a small number of transects or even individual transects. The Bayesian approach uses information from the current measurement and a prior estimation. The prior estimation in QRevInt is currently set to 3% with a 20% uncertainty. The coefficient of variation computed from the measurement is used for each transect to compute the total uncertainty associated with each transect. Now let's look at the Uncertainty tab in QRevInt. The table at the top shows the uncertainty of all the components used in the RSIN uncertainty analysis for each of the transects and as a total for the measurement. Below the table are 2 additional graphs. The first graph shows the contribution of the cell size, the water velocity, and the boat reference to the measured discharge uncertainty, which would be this column, which is typically small. The graph at the right is essentially the same graph as the lollipop plot on the main page, except in this situation, not only do we show the contribution to the total uncertainty for the measurement here in the all column, but also the contribution of each component to the total uncertainty for each of the transects. Finally, the user could override the estimated uncertainties for any of the components, and then that user-specified uncertainty would be used in the computation of the total uncertainty. In addition, by clicking on the Advanced Settings tab, we see the various defaults for the RSIN approach, and also a column where the user could set different default values for each of these components and then use RSIN to compute the uncertainty based on those changes in the default components. Returning to the measurement that we have been using in our examples, we can look at the uncertainty first from the QRev uncertainty model, and we see that the estimated uncertainty is 7.2%. Click on the Options menu, scroll down, click RSIN, open that up, and we can see that the RSIN method estimated an uncertainty of 6.3%. The RSIN approach does give us additional detail, and we can see that invalid boat velocity contributed the most to our uncertainty, followed by random error measured by the coefficient of variation, and then systematic error, which we really can't do much about. So, which model do you choose for your uncertainty analysis? That is up to your agency. However, I would suggest that your agency select a model and be consistent with the model that's being used. Uncertainty is currently a hot research topic for many researchers, and it is expected that additional models and improved models will be introduced to QRevInt in the future. That wraps up our discussion of uncertainty.